Hello everyone, I am Jerome Govinden, and I will be presenting our paper on the indifferentiability of the duplex and its practical applications. This is a joint work with Jean-Paul de Gabriel and Mark Fischlin. In this work, we provide a new treatment for the duplex indifferentiability. My talk will be divided in 3 sections. I will start by giving some background that will help to understand the need for new treatment of the duplex indifferentiability. Then I will follow with our main result, which is the indifferentiability of the duplex from a new idealization, which we call the online random oracle. And finally, I will show how this indifferentiability result can be used to prove strong executive notions for duplex-based AED, and how it can have other practical applications. Let's start with the background. Most security analysis focuses on indistinguishability, which consists of proving a specific property for construction C. In this game, an adversary D tries to distinguish between a construction C in the real world and an ideal function R in the ideal world, which represent a specific security property. The construction C can depend on an ideal public primitive P, which is then accessible by the distinguisher in both worlds. We then say that the game is in the P model. However, indistinguishability has a limitation that it can be proven only for keyed constructions. The indifferentiability framework by Morer et al. Serves a different purpose, which is to build a higher level ideal primitive R from a lower level one, here P. The difference with the previous game is in the ideal world, where D doesn't have access to a primitive P, but to a function S simulating the primitive P. An advantage of indifferentiability is that it can be proven for unkeyed construction, and that it also covers multiple security properties embodied by the ideal function R. This is due to one of the main properties of indifferentiability, which is composability. The composability theorem says that if C is indifferentiable from R, then in the P model, it has the same security properties as R. Indeed, to prove security of a construction C for a certain game G, indifferentiability allows us to replace C with R and P with S. And then, if we combine the adversary A and the simulator S, we obtain a world where this combined adversary A prime needs to play the game G for the ideal function R. Concretely, if you take the full domain hash example, if you want to prove on the left that full domain hash based on the sponge is secure, you only have to prove that the sponge is indifferentiable from the random oracle, and that on the right, full domain hash is secure in the random oracle model. And an important requirement to be able to apply composability is for the construction C and the ideal function R to share the same interface, meaning to have the same number of inputs, which needs to be of the same type, and similarly for the outputs. Then the game G can interact with them in the left and the right game in the same manner. Some examples of this are the random oracle with respect to hash function constructions, such as the sponge, for example, or the ideal cipher with respect to block cipher constructions, such as the 5-cell network or the key alternating cipher. In the case of authenticated encryption, Barbosa and Farshim gave random injections as idealized model. Very importantly, in all these cases, the primitive and the idealized model share the same interface. And when the indifferentiability of a primitive is studied, it is always done with respect to a specific idealized model that shares the same interface. The problem we studied in our paper is which idealized model would fit to the duplex. To understand why this problem is relevant, we need some more background on the duplex. The precursor of the duplex was a sponge construction, which is the basis for multiple NIST standards, and is based on a public random permutation P, which is applied repeatedly on the state. And then it starts by taking as input a message X, which is padded into block of equal length R, called the rate. Then each block is absorbed R bit at a time by the random permutation P. After this process, called the absorbing phase, comes the squeezing phase, where R bit at a time of the output of the random permutation P are concatenated until an output Z of the required length is obtained. When P is assumed to be a random permutation, the sponge construction is indifferentiable from a random oracle. The security of the construction lies in the secrecy of the capacity part of the state, which are the C-bit part of the state that are not returned to the adversary. The duplex construction is a different primitive derived from the sponge that allowed the construction of one-pass AED schemes. It is in fact the basis of multiple AED candidates of the Caesar and NIST lightweight competition. It has two distinct interfaces, an init and a next interface. The init interface initializes the state of the duplex to 0 and takes an input x0 of size r bits that is sold to the first r bit of the state. Then it applies a permutation p to the state and returns the first r bit of its output. The next interface is similar to init, but doesn't reinitialize the state to 0. And while the sponge was stateless, the duplex is a stateful construction, meaning that the state is conserved from one call to the other. Here in the picture, from init to next, and from next to next. To be noted, the duplex supersedes the sponge, as the sponge can be represented as a special form of the duplex, while the duplex still has more functionalities. Yet, when its security was first analyzed, it was still argued through the security of the sponge. In the analysis of Bertoni et al., an instance of the duplex was reduced to a sequence of sponge calls. For example, for the following instance of the duplex, the first init call with input x0 is mapped to a sponge call with one input block x0. The second call to next with one input x1 is mapped to a sponge call with two input blocks, x0, x1. And then the same goes for the third call, with now three input blocks to the sponge. And then, using the indifferentiability of the sponge from the random oracle, it was then argued that you could reduce an instance of the duplex in the ideal permutation model to a sequence of random oracle calls. While this analysis was on the n-key duplex, follow-up work focused on the indistinguishability of the key duplex, which is the duplex where the initial state is filled with a secret key k. This analysis led to better bound compared to the unkeyed case, and also to an improved version of the duplex called the full state key duplex, with improved absorption performance, where now the full state of R plus C bit is absorbed, but still only R bit is squeezed. And while the duplex was originally needed for AED, its versatility was then recognized to build other applications, such as online hash, which is a hash function that can be accessed in an online way, meaning that after computing a digest for first input, one can append a second input to it and obtain a new digest without the need to process the first input again. This is used in the noise protocol framework, for example. Other examples of applications are MAC, symmetric ratcheting, and pseudo-randomness generation. And all this functionality are implemented in the strobe protocol framework, which is a library based only on the duplex. And as you can see, some of these applications are unkeyed. And the problem that arises is that recent security analysis of the duplex abandon indifferentiability for indistinguishability, meaning that they prove security for specific usage and not for a general purpose primitive. But now that indifferentiability is needed again, we need a clean idealized model for the duplex, which will also be useful for developers of libraries such as Strobe to have a clean mental model of how to think about the duplex. We have therefore studied the indifferentiability of the duplex. But let's first take a look at the previous unkeyed security analysis from Bertoni et al. It has multiple limitations. The first one is the mismatching interface between the duplex calls on the left and the calls to a random oracle on the right. which prevents a direct application of the composition theorem. Indeed, as shown in the figure, the call to the next interface of the duplex takes as input a single block, whereas the corresponding call to the random oracle takes 2 or 3 blocks as input. This mismatching interface led to the need for an extra step to transform the duplex into a sequence of sponges, which makes any analysis more complex. And due to the need of this transformation into sponges, any limitation of the sponge is imposed to the duplex. For example, as the sponge needs padding for its security, it imposes to the duplex a sponge-compliant padding at every call to the permutation P. Yeah. And this is an important limitation that doesn't cover practical usage, as most practical duplex construction drop this padding without justification. But as our result will show, this padding is not necessary for the security of the duplex. And to overcome this limitation, we then define a new idealized model for the duplex, which we call the online random oracle, or ORO for short, that shares the same interface as the duplex. The ORO is a natural adaptation of the random oracle to a stateful primitive that can be interacted with in an online manner. To briefly describe how it works, to each query, we associate a path, and we keep a table for mapping paths to answers. And the path corresponding to an init query is its given input x0, and the path corresponding to a next query consists of the concatenation of all the input queried since the previous call to init, here x0 to xi. Then the answer associated with a path is sampled at random only once, when it is queried for the first time. When a path is repeated, the previously sampled corresponding answer is returned. Furthermore, because the ORO is a stateful shared object, we need a way to separate queries from one party to another. This is usually not a problem for a stateless primitive, but it is for a stateful one. And to do so, we've updated the syntax of the ORO and the duplex to support multiple concurrent sessions through a session ID, bringing it closer to practice. And as a positive result and the main contribution of the paper, we then show the indifferentiability of the duplex from the online random oracle up to 2 to the C over 2 queries, C being the capacity of the duplex. The proof we give is done using the code-based framework from Bellare-Rogoway with a careful quantification of the resources of our efficient simulator. As an added advantage of our result, we obtain indifferentiability for a version of the duplex that doesn't require padding at every block. A natural question that arises is, could we say something similar for the full state duplex, which is the improved variant of the duplex with full state absorption? In this case, it is not possible to show indifferentiability, as exemplified by the following attack. The main idea of the attack is that in the real world, for any x, we can evaluate y by querying the permutation oracle. Then, as the duplex is full state absorbing, one can come up with 2 pairs y prime and ww prime that will lead to a collision. While in the ideal world, this input will correspond to 2 different paths that will lead to a collision, only with small probability. And despite this negative result, the indifferentiability of the classical duplex can have multiple practical applications. One of them is for AEAD. The classical template for building AEAD schemes from the duplex is SpongeWrap, here represented in its nonce-based version. The detail of the figure here is not important for this talk. What is important, however, is that SpongeWrap, until now, satisfied only plain AEAD security. Thanks to our indifferentiability result, we were able to prove stronger security for this variant of SpongeWrap. To achieve this result, we first proved the following stronger security in the ORO model. We start with the key-dependent message security, meaning security when the message M, encrypted, can be a function of the secret key K. This security is especially useful for disk encryption, hardware security module, and key management system, where a secret key can be used to encrypt another one. We then prove security against related key attack, where the adversary is able to obtain ciphertext evaluated under a modified K prime that is a function of the secret key K. This is useful to model fault injection attack. And finally, we prove full context commitment security, with, to give a few, applications in message trunking and key rotation. All these stronger security notions were first proven in the Oro model here, and were only possible to prove because one of the characteristics of the Oro model is that it makes proof simpler and more intuitive. Moreover, as the Oro share the same clean interface as the Duplex, it allows a straightforward application of composability to translate the previous security result in the random permutation model. And by doing so, we bypass a complex, dedicated analysis of spawn drop in the random permutation model. And we obtain the first one-pass EAD scheme to achieve KDM, RTA, and commitment security. Indeed, to our knowledge, all previous secure constructions for these notions require 2 or 3 passes over the data. And while the applications we looked into were mostly AEAD, other practical applications of our indifferentiability result, suitable for future work, could be to prove KDM, RTA, and commitment security for other primitives based on the duplex, such as pseudo-random functions and math. Or to use the Oro model to prove more easily security for upcoming stronger security notions, especially new AED security notions. Or finally, prove the security of protocols built from multiple instances of the duplex, which can be keyed or unkeyed. For example, security of protocols constructed from the NORS protocol framework. So this concludes my talk. I thank you all for your attention, and the full version will be available soon on ePrint.